Hi, in this video I will give you a brief overview regarding the functionality of my 2014 VCE Systems Engineering project. The project and its origin. This year I have created a computer-controlled unmanned aerial vehicle, or UAV for short. It features a camera along with a miniature water cannon to demonstrate a firefighting use case. I conceived this project in late 2013. Many systems engineering projects are made just for fun, and there's nothing wrong with that. However, I wanted mine to have a purpose. From the start, I knew that I wanted to make full use of my skill set, which includes comprehensive software development knowledge. Throughout the year, I created two sub-prototypes which I could fly, namely a small 3D printed micro quadcopter with a custom control circuit, and a medium-sized model using commercial parts. 3D printing. I was extremely lucky to have access to a 3D printer via my school who paid for the printer itself as well as consumables. 3D printers create models designed in CAD via plastic extrusion, whereby the model is created layer by layer. I designed nearly every part of my chassis from scratch. This allowed me to incorporate off-the-shelf components in a very aesthetically pleasing manner. It also streamlined the assembly process as the accurate parts could interlock using machine screws. There were two major challenges with this technology. First of all, I had to learn how to use CAD software from scratch. I always had to take into account the nature of 3D printing, for instance, avoiding overhanging parts which require messy support material to print. Secondly, I was working at the printer's limits due to the large parts I had to create. To ensure good quality prints, I had to re-engineer the print bed to ensure the plastic parts did not warp as they cooled. Drivetrain. The UAV I created uses a multi-rotor drivetrain system with very few moving parts. Traditional helicopters require a mechanism to change the pitch of the blades in order to maneuver the vehicle. In contrast to this, a multi-rotor system varies the motor RPM and relies on unbalanced forces to propel the vehicle in the desired direction. I have used 4 brushless DC motors arranged in an X pattern with over 500 watts of power each. They are coupled with 14-inch carbon fiber blades. Power comes from a high-performance 6-cell lithium polymer battery. At full throttle, the drivetrain can produce about 3 horsepower. This is very dangerous. Hence, I've had to take many safety precautions, for instance, throttle limiting. Such a powerful drivetrain is required due to the weight of the vehicle, which is nearly 3 kilos. The drivetrain has been over-engineered to cater for future upgrades. Communications and control. Unlike other quadcopter projects that use an off-the-shelf remote control system, I have developed mine from scratch. This is only possible due to my extensive software development knowledge. The model is designed to be flown remotely via a computer coupled with a USB flight joystick. Currently, communication with the model and base station is conducted via Wi-Fi. This link is also used to provide a live video feed from the onboard camera. There is scope to use a mobile data network for the communications link, which could allow for greater range. The computer control software was written in Visual Basic 2013, and communication occurs via the HTTP protocol. On board the vehicle, there is a Raspberry Pi computer coupled with an Arduino control circuit. The Raspberry Pi is running code written in Python, and Arduinos use a C-based language. I have created custom circuit boards to control the various lights and mechanisms on the vehicle. The drivetrain is controlled via a commercial flight controller which receives data from the Arduino circuit. Onboard subsystems. The vehicle includes 3 peripherals, namely a miniature water cannon, an onboard video camera, and an emergency lighting system. It also includes other sensors, a radio altimeter, GPS, altitude sensor, and an accelerometer. The water cannon was created using a small 12-volt pond pump inside a custom 3D printed tank enclosure. There is scope in the design to allow for remote refilling using an external pump, similar to the famous Elvis firefighting helicopter. The onboard video camera is coupled with the Raspberry Pi and sends a live video feed to the computer base station at a resolution of 360p. It can also capture high-resolution still images. The emergency lighting system was a last-minute addition. This was because I had to split the Arduino control circuit into two parts due to a lack of I/O. It features red and blue flashing lights and white headlights, which can be dimmed to mimic high and low beam. A piezo buzzer is also included to simulate a police siren. Conclusion and alternate use cases. There are various other use cases for this technology. It is important to note that the multi-rotor drivetrain is only a platform and can be replaced with alternatives such as a land-based rover or fixed-wing aircraft. I have simply chosen the multi-rotor platform due to its mechanical simplicity and research gathered from previous projects. Every day, tasks are undertaken using manned vehicles. One major example of this is daily traffic spotting. More often than not, this is conducted using a manned helicopter and manual spotting techniques. This is very time consuming as it is expensive to scale a fleet of such vehicles, hence the job can only be completed by a few operators at any given time. If we were to adapt my system to this use case, it would not only result in enormous fuel savings, but we could also vastly increase the scope. Fleets of UAVs could be dedicated to particular arterial roads to gain a greater level of detail regarding the traffic situation. Not only would this benefit drivers, but it would also allow engineers to have more data readily available for planning of future projects. And finally, here's something to ponder. What would you do with this technology?